Hello guys, welcome to the machine design world. This is Keval Patil and today we are going to see design of lip spring with using PSG. In last videos we have seen the design of helical springs. So today we will start with lip spring. Let's start with introduction of lip spring and terminology associated with the lip spring. Let's start with introduction, and for lip spring PSG page number is 7.104. Okay, first thing is lip springs are also called as semi-elliptical laminated springs or laminated springs. Okay, so this is a diagram of semi-elliptical lip spring. Okay, so first of all, see, this is a master or main leaf. Okay, they are having number of leaves. You can see number of leaf, so gradually length is increased. Okay, this leaf, first leaf, which having this curved section called as spring eye, okay, called as main or master leaf, main or master leaf. So first spring, first leaf called as main or master leaf. Okay, again all other leaves, you can see all other leaves are bolted to this master leaf. Okay, or they are bolted together. U bolt is used. Okay, this is U bolt, and one more bolt at center is called a central bolt. Okay. Now after main leaf, you can see two leaves having same length. They are having same length. They called as extra full length leaves. Okay, usually 2 to 3, or you can say usually 1 to 3 extra full length leaves there. We denote it as NE. So number of extra full length is NE. Okay, so this two leaves which having same length, and other leaves you can see their length is gradually decreased, or from this side it is gradually increased. They are called as graduated leaves, and number of graduated leaves is NG. Okay, so hopefully you understood this diagram, okay, or the structure of lip spring. It is having U shape bolt or U bolt centrally, or one central bolt to clamp this all leaves together. Okay, now first leaf is main or master leaf, then we having extra full length leaf, okay, and then we having graduated leaf. This is nothing but rebound clips. Okay, they are along with the length of the spring, so that the graduated leaves share the rebound load with main and master leaf. So whenever there will be rebound load, they will share it with master leaf. Okay, so I think terminology is over. Okay, and one term is remaining, that is camber. Okay, so camber is nothing but, you can see each leaves are initially curved. Okay, each leaves are initially curved, and this initial curvature is known as camber. Okay, this initial curvature is provided so that the leaves will tighten. Okay, when we will apply load from this side, this side, what will happen? They will try to straighten. Okay, so that's why this initially curvature is provided. So under the application of load P, they will try to straighten. Okay, this P. So if we having 1000 Newton load, okay, on lip spring, okay, then that 1000 Newton load is divided in such a way that half of the load will act here and half of the load act here. So 500 Newton here and 500 Newton here. That's why having P Newton load here and P Newton load here. Okay, so total load on spring is P plus P, 2P. Then this distance from the center of the bolt to the center of the eye is known as L dash. Okay, and this is also L dash, and the total length is 2L dash. So this length L is called as ineffective length, okay, or clamp length. Actually, why it is ineffective length? Because this area is fixed. It is fixed means it does not contribute in any energy storage. Okay, whenever this load is acting, it tries to straighten, but this area is fixed. So it is fixed, so it does not contribute in energy storage. So that's why it is ineffective length. So this area is ineffective, so that length is ineffective length. So what is effective length then? effective length is L dash plus L dash minus L. That is nothing but 2L dash minus L. Okay. So we will see few nomenclatures. Okay. So 2P is the total load on the spring, P plus P. Okay. Under the application of load, there will be deflection of the spring. There will be the deflection of spring. That is Y. 2L is the effective length of the spring, and it is equal to 2L dash minus L. So it is effective length 2L. 2L is equal to 2L dash minus L. L is ineffective length. Okay. Sometimes in problem value of L is not given, so it is considered as 80 mm. Okay. If it is not given, then 80 mm most probably they give it. Okay. Now L is a clamp length, that is ineffective. T is a thickness of leaf. Each leaf has thickness. Okay. This thickness is called as T. Okay. They are having same thickness. B is the width of the leaf. If this is a small section of the leaf, then this B is the width of the leaf. This R is a, they are having curvature, right? So this is a nothing but radius of that curvature, right? Now we know that extra full length leaf, any number of extra full length leaf, and NG is number of graduated leaves. So NE and NG. So total number of leaf will be N, and that will be NE plus NG. So N is equal to NE plus NG. Okay, this is NE plus NG. Alright. So hopefully you understood the terminology. Now we will go for the problem. Before going to the problem, we should understand why we should use this lip spring. So first of all, everyone knows where we use this lip spring: in automobile. In automobile, if you see trucks, then you can easily recognize this lip springs. Okay. And why we are using lip spring when we are having helical spring? So advantage of lip spring over helical spring is it acts as a structural member, means it supports the load. Okay. And it, addition to absorbing energy, it supports the structure. Okay. And it is capable of taking lateral load, again braking torque, driving torque, and additional shocks or vibrations. Okay. An application we know, automobile suspension. Material usually lip spring uses oil hardened and tempered alloy steel. Okay. And material of the lip spring is not that much superior as helical spring, but then too we use the oil hardened and tempered alloy steel like 50 chromium L, 50 chromium V23, etc. Okay. Now we'll move to the problem. So this problem was asked in Mumbai University question paper last year. Okay. So it reads: semi-elliptical lip spring is used for the suspension of rear axle of the truck. It consists of 2 extra full length leaves. Means number of full length leaves are NE, extra full length leaves 2. Okay. Leaves, and 10 graduated leaves. Number of graduated leaves are 10, including master leaves. Okay, including master leaves. Okay. So total number of leaf N is equal to 10. Alright. The center to center distance between the spring eyes. Okay, center to center distance between the spring eye means spring eye and center to this center to this center. So total distance is given, 2L1 dash is given. It is given as 1.2 meter. The leaves are made up of steel whose yield stress or tensile strength is 1500 Newton per mm square, and Young modulus is 27000 Newton per mm square. Factor of safety is 2.5. Now after this spring is to be designed for the maximum force of 30 kN. So here what is given exactly? It is given 2P is given. 2P is 30 kN. Okay. The leaves are pre-stressed. Okay. Leaves are pre-stressed so as to equalize the stresses in all leaves. Means they are pre-stressed. What is pre-stressed? That we will see. But here important point is they are having equal stress in all leaves. Okay. What that mean? I already told that lip spring you will get on PSG page number 7.104. Okay. Now see, we having 2 sets of formulae over here. First one this and first one is this. This formula, okay, treating the spring as cantilever beam of uniform strength. So this should be used when we having equally stressed leaves. If we having equally stressed leaf, then we use this formula. And another set of formula, this is what sigma b and deflection. Sigma b and deflection. Another set of formula, spring with extra full length leaves, means if there are extra full length leaves provided and they are not having equal stress throughout, means they are not having equal stress in each leaves, then we should use this formula. Here we having sigma bg, it is nothing but bending strength in graduated leaf, and here sigma be, that is bending stress in extra full length leaves. Okay, so now you can see this term is same, PL BT square, and this is same, PL BT square 3, and this is same, only 12 and 18 is different. So this is a bigger value. So in extra full length leaves we are having higher amount of stress than BG. So this is a design criteria. So we will use this as a design criteria, and then we will find the deflection. Okay, in Y term E is missing from here. You can see here 6PL cube upon E and BT cube. So it should be E BT cube into bracket 3 NE plus 2 NG. Okay, so here E is missing, so you can add E over here. Alright, so when we should use this formula? When we are having equal stress in every leaves. And when we should use this formula, then when it is not mentioned that spring having equal lengths. In that case, this extra full length leaves will carry higher amount of load than graduated leaves. Next is determine the cross section of the leaves, deflection of the end of the spring, and length of the all leaves. Okay, we will see one by one. First of all, what is given? 2P is given as 30 kilonewton. Total load is 2P, 30 kilonewton. So P is 15 into 10 raised to 3 Newton. Total length given, that is 1.2 meter. See, the center to center distance between the spring is 1.2 meter. So total length is 2. L dash is given 1.2 meter, that is 1200 meter. NF, it is given, it consists of 2 extra full length leaves, means we having NF is equal to and E is equal to 2. Actually it is not NF, and E is equal to 2. Then graduated leaf including master leaves, 10 graduated leaves, so NG is equal to 10, and one among it is master leaf. Now E is equal to 20700 given, factor of safety 2.5 given, sigma YT 1500 given, and L is given over here. Consider ineffective length of 80 mm. If it is not given, then you have to consider it as 80 mm. So 80 mm is given. We know that effective length 2L is nothing but 2L is equal to 2L dash minus L. It is nothing but 120080. You will get 1120 mm. So 2L is equal to 1120 mm. What will the L? 560 mm. Now we will find the allowable stress. We know the tensile stress is given, divided by factor of safety. You will get allowable bending stress. So tensile yield stress is given, divided by factor of safety 1500 divided by 2.5, that is 600 Newton per mm square. So I think this much is, you have understood this much part. Now we will move to the PSG work. So it is mentioned that all leaves are gradually stressed. So we should use first set of formula on PSG 7.104. So this is the first formula. It is given in PSG. It is given in PSG sigma b, this formula, and this formula we are going to use. Okay, so it is 6PL upon NBT square. So sigma b we know 600, just now we saw 6 into P is 15 into 10 raised to 3, L is 560, N is number of leaves, that is 12, B is we don't know, T square we don't know. So with this we have to find B and T value. Sometimes B's value is given and sometimes it is not given. If it is given, then it is alright. If it is not given, then consider it as a 60 mm, which is assuming standard width B is equal to 60 mm. So from this equation you will get BT square is equal to 7000. Alright, so now in this sum it is not given, so we are considering the standard width, that is 60 mm. So from here you will get T is equal to something 10.8 mm. You can take it as level mm. Now next formula, that is deflection of the spring. Y is equal to 6PL cube upon En BT cube given in PSG 7.104. Just put all the formula, all the values, 6, P value, L value 560, E value 2 given, and 12, B value just we saw 60 mm, T value just we found out level. Then you will find Y is equal to 79.67 mm, that is nothing but 80 mm. Alright, next we will move to the design eye of the master lip. Okay, see, this is the master lip, right? So we having this master lip, and this is the eye of the master lip. So this is same as eye of the master lip. Okay, so this is eye of the master lip. Actually, this master lip eye, we put one pin, okay, this long pin in the master lip eye, and it is supported like this. It is supported from both the side. Okay, so it is nothing but simply support. Okay, simply supported pin or simply supported beam, you can say. So this eye, from both the eye, we take one pin outside, okay, or we put one pin in the eye and then we support it from outside. Okay, so it is simply supported. It is supported over here, and it is also supported over here. Alright, now what load is acting over here? P load is acting over here. What is this? This length is, we know this length is width of the leaves, that is B. There is some clearance over here, there is some clearance over here. Okay, then it's a small clearance. dP is a diameter of pin, or you can say diameter of inside eye. Okay, now this is simply supported beam, so we know that for simply supported beam, what is the bending moment? Moment is WL by 4. So WL by 4, we having P over here, so it will be PL by 4. So what is formula for sigma B? MB by Z. M is equal to PL by 4 or WL by 4. And what is Z? Z for circle, or it's a bending moment. We know that formula for, we know this formula, simple moment equation, simple bending moment equation. May I serve you, Elizabeth? And this is short trick to remember. So I'm using this. So M I by Y is equal to sigma. So it is nothing but sigma P. I by Y is nothing but Z. I is the moment of inertia. Y is the distance of outer fiber from centroidal axis. So it is called as Z polar section modulus. Sorry, not polar. So it is nothing but pi by 32 dP cube. Okay, so now we having everything. We have to find dP, but sigma B we don't know. So we have to consider the material for pin. It is nothing but simple small shaft. So we'll consider plain carbon steel as a material. So I'm considering C30 as a material. Okay, from PSG 1.4, 1.9. Okay, PSG 1.9. I can get this value. Sigma Y is equal to, for C30, sigma Y is 300 Newton per mm square. Now it is simple shaft. Okay, I'm just considering high factor of 50. You can consider 4 to 8. I'm just considering 4 factor of city as 4. So sigma B will be 300 by 4 is 75 mm. So just put 75 over here. W is nothing but P, that is 15,000. L here, L is equal to B. I'm just considering this clearance as negligible. Okay, so I'm just considering as 60 only. So 60 divided by 4 and pi by 32 dP cube. So from here you will get dP value as 4.5. I'm just considering, it is shaft, so I'm just considering the next even number, that is 16 mm. Okay, so dP is nothing but is equal to d. D is what? Diameter of eye. So this diameter of eye is equal to diameter of pin. Okay, so it is easy, I think. Alright, so now we will move to the finding calculation of length of the leaves. Okay, now this formula, this is the length of the leaf formula, 2L upon n minus 1 number of spring, like first leaves, second leaf, third leaf, fourth leaf. Okay, from down. Okay, from down, we measure from down. So this is the first leaf, second leaf, third leaf, fourth leaf, like that. Okay, so this is formula for the length, leaf length. Okay, so Ln is equal to 2L n minus 1 nth number of leaves, then plus clearance. Okay, this is not in PSG, you have to remember this. Okay, so if you put 1 over here, so this is length of first leaf, so L1 is equal to 2L value we already know. Okay, so 2L value is level 20, so it is level 20. N minus 1 number of leaves, 12 minus 1, okay, into nth is first, so into 1 plus 80, so you will get first length of leaf is 181.8 mm. Similarly, you just put 2 over here, so L2 length of second leaves 2, everything else is same, so 283.6. Similarly 3, and you will get all the values. Okay, so L4, L5, L6, L7, L8, L9, L10 and L level. There are 12 number of leaves. Okay, so L4, you just change this value with 4 and you will get L4. Change with 5, you will get L5. Similarly, you will find L11. Okay, but we are not finding L12. L12 is what? Master leaf. Master leaf having these eyes. Okay. Now length of the master leaf. So length of the master leaf, again I am telling L1 dash plus this length plus this length. Okay, so we have to consider this length total plus this length. Okay, so this is 2L plus L, it is nothing but 2L dash plus 2 pi d plus t. So 2 pi is, you just don't consider this, pi dt, d plus t is, this is d. Okay, this is diameter d plus this t. Okay, so I'm just finding this perimeter, so it is pi dt. Now we're having this one and this one, so that's why it is 2 pi dt. Don't consider half. Okay, we are just considering this total length. Okay, this total length, it is nothing but perimeter. We are not considering this length, we are considering perimeter, this total length. We want to find this total length. So we already found this length, we want to find this length. This we considering it is full perimeter. That's why 2 pi dt, pi dt plus pi dt. Okay, sorry, pi d plus t into plus pi d plus t, it is 2 pi dt. Now 2L plus this we know that is nothing but 1200 plus 2 pi d we found out 15 plus t is 11. So from here you will get length of the master leaf. Actually your problem ends here. Okay, all the terms we found out, but sometime or they may ask for radius of leaf or initial bend. Okay, so we are having this leaf and it is bent, so this is radius of bend. So this radius of bend formula is y is y into bracket 2r minus y, here r is the radius of bend, minus y is equal to L dash square. Okay, so y we know, deflection, so it is 80. Just put the all values over here and you will find r is equal to 2290. Most probably they won't ask it, but if they ask, then you have to find using this formula. Again, this formula not in PSG. And the last term remaining, that is nipping gap. So first we will understand what is nipping. See, usually stress in the full length leaves is 50% more than graduate leaf. Means if graduate leaf having 100 stress, then full length leaf has 200 stress. Means stress is more in graduated leaf. So it is actually stress is more in full length leaves. Actually they are taking more load. Okay, but we have read in the problem that they are pre-stressed so that they are having equal stress. So in order to best utilize the material of the spring, okay, material of the each leaves, every leaf or each leaf should have same stress value. Okay, so it is achieved by pre-stressing. We already read in the question. Okay, so pre-stressing. So what is pre-stressing exactly? Pre-stressing means we give extra radius to the graduated leaves than the full length leaves. So let's get full length leaves having 100 radius, so graduate leaves will have 120 radius. So how it matters? Okay, see, this is position when there is no bolting. After bolting, what will happen? After bolting, they will come together and they will have same radius. Okay, after bolting they will tighten or they will stress together and they will have same radius. But so when we tighten this together, tighten with these leaves together with using bolt, what will happen? We are just stressing it in this direction, stressing full length leaf in this direction and stressing graduated leaf in this direction. Means the graduated leaf will move in this direction and full length leaf will move in this direction. But actually there will be stress because of this action, because of the bolting, there will be stress in this leaf and this stress will act in opposite direction. Stress will means this leaf is trying to go in this direction before application of this load F. Because of the bolt, tightening bolt, we just tighten them. So now it is having stress in opposite direction, it is trying to go in this direction. Okay, and this is trying to go in this direction. Okay, when we apply the load, okay, what will happen first? After application of this load, what will the action of the spring? Like this, action of the spring like this. Already this spring is trying to go in this direction, so what will do? It will release, or it will relieve the initial stress. This X amount of initial stress is there, it will relieve the initial stress. And what will happen with this? It is already having this direction, okay, already having stress in this direction, and you again moving it in this direction, there will be extra stress in this direction, okay. So this will add something X plus whatever stress we're having, this will add, and this will, what happen? This will subtract from the stress. So now total stress developed in this will be equal to this stress, okay, because it is already taking 50% more load. So in order to have same value of stresses in each spring, we take small radius for full length loop and relatively larger radius for graduated loop, okay, and this is called as nipping, okay, and this gap between the two leaves is called as a nipping gap, okay. And now we want to find this nipping gap X, and it is nothing but 2pl cube upon NEBT cube, okay. This is the formula, just put the values, we are having all this value, put this value, and you will get the value of nipping gap X, okay. So I don't think they will ask anything more than this, okay. Only difference is if pre-stressing is not mentioned, that every leaves are not having same stress, in that case you have to use this formula. In these two formulas, use sigma B because it is having higher load value, so use sigma B, that is 18pl cube upon BT cube. This stress you have to use, this stress you don't have to use this one, and Y formula, Y formula, just add E over here and use this Y formula, okay. So in place of N, it is 3NE plus 2NG, 3NE plus 2NG, 3NE plus 2NG. Nothing difference. All other procedure is same. Okay. Hopefully you have understood today's lecture. It is a leaf spring. Okay. If you have any doubt, just comment and let me know. Okay. Thank you.